Here we go. We're going to be talking about endothermic and exothermic today, doing some calculations and then relating that to bonds breaking and bonds forming. So when I break a bond, I need strength. So I need to take energy in for that to happen. Endothermic. So remember, endothermic is the heat is taken into the reaction. So your thermometer actually goes down because your thermometer is measuring the surrounding water. Exothermic or other solution. Exothermic, exo, exits. So the heat is coming out. So on a fire or hydrocarbon combustion, that's going to be exothermic. It's releasing heat. And so the temperature is going to go up. So if you have a fireplace in your room or even you turn on the stove, that is exothermic. That energy is going to make the thermometer go up and it get warmer. Okay. So endothermic is positive for chemistry. So it's greater than 0. Okay, and delta H is just the enthalpy of the reaction. So as that reaction is endothermic or exothermic, you will see those positive and negatives. Okay, and if it's exothermic, it is negative. It left the reaction. In chemistry, we're concerned with the reaction. So we're talking about if I take energy in, that's a positive. If the energy exits, that's a negative. It left. Okay. So when I look at this reaction here, I notice this energy is on the reactant side. That means it's an ingredient, so it was used. So that is endothermic. It could also just be listed as delta H equals 285.8 kilojoules. Now let's look at that in terms of bonds breaking and bonds forming. So we have 2 Mickey Mouse molecules here. Why do I have 2 of them? Because I have 2 moles of water. So it's easy just to show that as 2 sets of water, or your hydrogens are your ears. And your oxygen is that nose. How many bonds do I have here? I have an HO bond, an HO bond, an HO bond, and an HO bond. So I have 4 HO bonds on this side. What about on the right side? I have 2 hydrogen gas and 1, oh, can't see that, and 1 oxygen gas. That oxygen gas is a double bond, so you do want to be aware of that. These are not Lewis dot structures. These are just quick and dirty so that you can make sure you're not miscounting the bonds. If you're like, oh, I don't remember how to draw oxygen, then yeah, do the whole setup. Okay, 6 valence electrons, so 2 bonds. So 4 here and 4 there, and just double check. Okay, 6 plus 2 is my octet for 8. And 6 plus 2 is my octet for 8. So do something just quick of drawing to make sure that you have the correct number of bonds, because we need to count how many of each bond. So on the right side, I have 2 hydrogen bonds, and I have a 1 oxygen double bond. And now I look down here, 4 hydrogen bonds, 4 hydrogen oxygen bonds, and on the right, 2 hydrogen bonds and 1 double oxygen bond. So I have 4 bonds on the left. Bond breaking is exothermic. Which side am I going to be breaking bonds? I'm going to be breaking bonds on the reactant side because I have to break them apart to put them back together. Okay. So those 4 HO bonds are energy that I need to bring into the reaction to break those guys apart. On the right side, I have 3 bonds made. Okay, and when I make bonds, energy is released. So if you're just looking at numbers, this is not 100%, but if you're just looking at numbers, I have 4 bonds were broken and 3 were made. So overall, I'm probably going to have more energy needed on the endothermic side. So in year 1, Oftentimes that is where we stop, but I'm going to go through and give you a little bit of the science in case they do give you your bond enthalpies to deal with it. And now, those three made, one is a double, so that is going to increase the amount of energy released because it's a double bond instead of a single bond, but it still comes out ahead that we have an endothermic reaction. Bond breaking is endothermic because it needs strength to bend the bond, so it has to take energy in to have that strength. Now we have the reaction going around on the other side. Is this endo or exo? I see the energy is on the product side. That means it's something I can collect, which means it was released from the reaction. So that is exothermic. It could also just be written separately as delta H is equal to negative 285.8 kilojoules. This time we're going to use the numbers. If you notice, I am just using the reverse reaction from the slide before. So before we were decomposing water and here we're synthesizing water. And so those guys are on opposite ends of the spectrum. So it makes sense that this guy is exothermic because he's opposite of what we did last time at endothermic. So I have my same little rough drawings right here, but now I have some numbers going on. So now I can start putting numbers to that. I have two HH bonds, and an HH bond is 436. And I have one OO bond, which is 498. So those are 2 at 436 plus 1 at 498. And that is going to be 13.7 kilojoules needed to break. Breaking bonds is endothermic. Okay. Endothermic is positive. And now we have over here, we have two waters. Don't just think about it as two waters, though. What does it have? 4 HO bonds. And the HO bond is 463. So 4 times 463 is 1852. Okay. Exited. So that's exothermic. So that is negative. Put those guys together. Okay, and I get an answer that is negative. So that confirms it is exothermic. Okay. There are a couple other things in year 2 you will learn about this, but this is just that starting working on this so that you can decide if something's endothermic or exothermic. Okay. How about if we're just given numbers and we're not so sure what's happening? Maybe it's just a phase change. In this case, it's just a phase change. Then we're not concerned with those bonds breaking and forming. So we're going to use this MCAT equation to answer that. Okay, 2 moles of water. So that is my N. Water is H2O in case I need it, is heated from 50 degrees. So that 50 degrees is my initial or my starting temperature to 75 degrees. So then 75 degrees is going to be my ending temperature. So my final temperature or my temperature 2. Is this endothermic or exothermic? So we need to figure out how much energy was actually there. Okay, if the energy is released and we get a negative, then it is exo. If the energy was absorbed in that phase change, then it is endo. Right? So let me see what values do I have. I'm going to solve for Q. I need a mass. I don't have a mass. I'm going to come back. C is the specific heat. It doesn't give me a number, but I know that the specific heat of water is 4.184 joules per gram degree C. So I have a specific heat. Change in temperature. I have 2 temperatures, so I can find that answer. 75 minus 50. So there we have that laid out. I need to have every spot filled. My mass is not filled, so I got to look back up here. What else is going on? Oh, I have a moles. I have 2.0 moles of water. Can I change the moles to grams? I can using molar mass. Okay. 2.0 moles of water over 1, start over 1, and I'm going from moles to grams. So the from always goes on the bottom, the to goes on the top. Grams to moles, that's my molar mass. And I know there's 18.02 grams is equal to 1 mole. 18.02 grams equals 1 mole. This is not a cross multiply and divide, it is dimensional analysis. So that is a multiply in between the two fractions. 2 times 18.02 divided by 1. So that just gives me 36.04 grams of water. Substitute, solve sig figs. 2 sig figs, 2 sig figs. So the number I'm going to use in the equation is 36 grams. Now I have an M, a C, and a delta T. So I can now substitute in to find my Q. 36 times 4.184 times 25. And always you can pause and do these with me. You can check that you're putting into the calculator correct. That gives me 3765.6. Okay. You can watch the videos many times as you need to make sure you have the answer. All right, 2 sig figs, 2 sig figs. Okay, why did I count this as 2 sig figs? Because we had to round to the least decimal place, not to 1 sig fig there, because when you add or subtract, it's least decimal place. So I am going to round my answer to 2 sig figs. So I'm going to round it to the nearest 100 because that's where my second sig fig line is. 3,800. Remember, it's not 38. 38. If I owed you $3,700 and I gave you $38 and said, oh, close enough because of sig figs, you would not be happy. It has to be in that same ballpark. 3,800 joules. This guy is a positive. So that means this reaction is endothermic. Okay, and the water was heated. If the water is going to be heated, it's going to be taking that energy inside. Double check that makes sense that it is endothermic. So if you don't see a chemical reaction, even though it's in moles, remember, use that molar mass to convert and then use your MCAT equation. If you're giving a chemical reaction, like what we did before, you have those bond enthalpies, or there's also stoichiometry you can do, which we'll handle in another video. So here's a coffee cup calorimeter. This is a standard lab that you would do. It's actually usually 2 or 3 coffee styrofoam coffee cups because that's cheap and easy with a lid on there. And the goal is to try to keep it as closed system as you can so that all the reaction or the physical changes that are happening in there can be recorded with the thermometer with the most accuracy. Okay, and notice we have a little bit of stirrer here that's not going to hit our thermometer. So it's a little bit of different designed thermometer or stirrer there. So it's insulated to reduce heat losses. And why do I want to reduce heat losses? So then we can use the conservation of energy equation. And as always, there's conservation of mass. So even though there's going to be some evaporating of the water, so you might have some changes, most of the time you're going to assume conservation of mass, because mass cannot be created nor destroyed. It could just leave the calorimeter. Now, if I put a heated piece of metal into the calorimeter with, or a cold, it doesn't matter. If I put something else in there, that's still just going to be a physical change. That heated up piece of metal is going to give off heat, and then the water temperature is going to rise So then our thermometer temperature is going to rise. And so we can use that to calculate all sorts of things. We can calculate masses, specific heats, changes in temperature, equilibrium temperature, because at a certain point, these two guys will be at the same temperature. Okay, the temperature of the water will equal the temperature of the metal or whatever substance you have there, and that's called at equilibrium. The temperatures have matched or are balanced. Okay, and so that's where we can come back in and use that equation to help us find all sorts of different information, including what type of metal we put in there, because we could solve for the specific heat of the metal to find our answer, right? So here is our equation when we're doing that. The energy of the water is equal and opposite to the energy of the other substance, because while one is heating up, the other is cooling down. So you need that negative in there to answer it. But any one of these guys can be solved for depending on what we start with. So let's see what we have. Wanda places water at 0 degrees C. Okay, that's the temperature of our water at the start. Okay, so lots of different information there. In a coffee cup calorimeter, then adds a 2 gram, okay, that's our mass of our metal, in this case, copper. And copper's specific heat, remember lowercase c is specific heat, copper's specific heat is 3.85 joules per gram degrees C at 50 degrees C. That is our temperature of our copper to start. So 1 being the starting condition. He records an equilibrium temperature of 40 degrees. 40 degrees equilibrium. What does that mean? Oh, that's when they became the same. So this is the temperature final for both the copper and the water, because we reached that equilibrium point. What is the mass of the water? So mass of the water. So lots and lots of little things right here. Okay, what is the mass of the water? So here's in a general form, but I can rewrite this. The mass of the water times the specific heat of the water times the change in temperature of the water equals negative the mass of the copper, the specific heat of the copper, the change in temperature of the copper. The mass of the water, we do not know. That is what we're solving for. So we know that's going to be our variable that's going to stay in variable form. Specific heat of the water, it doesn't say it, but we should know the specific heat of water is 4.184. So if it's not tell you, just remember 4.184. Change in temperature of the water. Do a little side quest so you don't get confused. The change in temperature of the water is the temperature final of the water minus the temperature initial or starting of the water. Temperature final of the water, I don't see it anywhere. I'm at equilibrium. The final temperature of the water is 40. The original temperature is 0. So that is 40 going in there for my delta T, or the change in temperature. The mass of the copper, so don't forget about your negative. The mass of the copper is 2 grams. The specific heat of the copper, 3.85. The change in temperature of the copper, change in temperature of the copper, the temperature ending of the copper minus the temperature beginning of the copper. Ending temperature is 40. Beginning temperature is 50. Go slowly, that's going to be negative 10. Why? The copper got colder, so he went down in temperature. He went to the left on the number line. The water got warmer, so he has a positive value. He added heat or added kinetic energy. Okay. So the change in temperature of the copper is negative 10. All right, mass of water, so I'm just going to leave that M right now, times 4.184 times 40 is equal to negative times 2 times 3.85 times negative 10. Combine like terms. 4.184 times 40 gives me 167.3 0.36 m. Why did I rearrange those? Just so it looks more like an algebra problem, because we got to access our algebra brains here. And on the right side, -2 times 3.85 times -10 gives me a 77, because two negatives equal a positive. The mass is connected to 167.36 by multiplication, so we got to divide. What we do to one side, we got to do to the other side. So my mass is 77 divided by 167.36. My mass is 0.46 mass. Grams would be our answer. Substitute, solve, sig figs. All right, so up here, 0 decimal places, 0 decimal places. So my answer is 0 decimal places. Over here, 0 decimal places, 0 decimal places, answer 0 decimal places. So those numbers I'm going to keep as is. Okay, and I'm going to check out my other sig figs. One sig fig here. So I'm going to round my answer to 1 sig fig. I don't put an underline with the 0. Why? Leading zeros are never important. Doesn't matter if there's a decimal right next to it. Leading, never important. So my 1 underline goes here at the 10th spot, or the 1 decimal place spot. So I'm going to round to the nearest 10th. I look next, it's a 6. So I'm going to round up 0.5 grams of water, right? And there we go.